In this section, we are going to study inverse functions. Let us first start with inverse relation. So we have here a relation. Take note, this is true for any relation, not just a function. If R is a relation from A to B, then the inverse of this relation is this set. The set of ordered pairs BA, where AB is an element of R. So take note that in order to get the inverse relation of a relation, all you have to do is to switch the first and second entries. And take note that if R is a relation from A to B, therefore, its inverse relation is a relation from B to A. For example, let us find the inverse of the following relations. R is this set, so therefore, what is its inverse relation? We just invert. This is B1, C1, and C2. I sub A, where this is the identity function on a set A. So therefore, what are the elements of IA? We also use the notation identity A, correct? And what are the elements of this? It contains AA, where A is an element of A, because recall that the identity function maps an element of A to itself. So therefore, what is the inverse relation? The inverse relation will be itself also, correct? Because when you invert, you still get this set. So this is still the identity function. What about the less than relation? So it contains, here my A and B are the set of real numbers. Let me just divide this. Okay. So this is saying, let me just write it as AB. So here we have R is equal to the set of all ordered pairs AB. Of course, you are in R2, R times R, where the first coordinate is always less than the second coordinate. What will now be your inverse relation? So since we are just inverting this, so we have BA element of R2 such that, so our B is now greater than A. That's the meaning of A less than B. Correct? So therefore, our less than relation is our greater than relation. How do we get the digraph of the inverse of a relation? So the digraph of the inverse of a relation can be obtained by just copying all the loops and reversing the direction of the arrows. Because remember that for our inverse, all we do is to invert the first and second entries. So for example, here is our relation on the power set of the set containing 1, 2. So we will have, this is 1, 2, we have 3, and then 1, and of course, the null set. We will still copy all loops, and we will just invert the edges. I will draw the arrows here. So here this is going that way, so it will be this way. This will now go to this one, and this one will go to this one. Now here is a theorem. Suppose that R is a relation from A to B, then the domain of the inverse relation is just equal to the range of the relation, and the range of the inverse relation is just the domain of the given relation. Let us recall that when we have a relation, the domain and range is still also defined just like with functions. So when we have R is the set of all AB, let's say. So let's just say, and then some rules here. Okay, so the domain of R is just the collection of all first entries. So my R here is a relation from A to B. So therefore, it's a subset of A times B. The domain of R, that's not the set of real numbers. This is domain of the relation R. It contains all first entries. So all A in A such that it is a first entry. So AB is an element of R for some B in B. So take note that the domain of R is just the collection of all first entries. So let me write it here, the domain of R. Again, this is not the set of real numbers. This is the collection of all first coordinates in the set R, and the range of R is the collection of all second coordinates. So meaning to say the range of R will be consisting of all B in the second set such that, again, AB is an element of R, but this time around for some A in A, because for you to be a second coordinate, there has to be a corresponding first element, correct? So let me just prove one. So for the proof of one, we are showing here that these two sets are equal. I will be showing that these two sets are equal by giving equivalent statements. So if we start with what will be an element in the domain of R inverse, it is a subset of what set? Is it a subset of A or a subset of B? Take note that R is a relation from R to B, so therefore R inverse is a relation from B to A, correct? So therefore the domain will be coming from B. Actually the domain is yes, coming from B. It is a subset of B times A. So if I get B and that is an element of the domain of R inverse, this is equivalent. In saying that, what does it mean for you to be in the domain of R inverse? It means that you are a first coordinate of a pair in R inverse, correct? You belong in the domain, so that means you are a first coordinate, so therefore you have to have a second coordinate. So BA, element of R inverse for some A in capital A. Take note that that is different from here because this is R. So what I just want you to remember when you're talking about the domain, you are the collection of all first coordinates. And if you are a first coordinate, then you should have a corresponding second coordinate. And the relation that we are talking about here is R inverse. Now, what does it mean for BA to be in R inverse? This means that AB is in R, correct? When we invert that. Again, we have for some A in capital A. But what does it mean? B occurs as a second coordinate and it has a corresponding first coordinate, correct? So this means that since B is a second coordinate of an ordered pair in R, it means that B is an element of the range of R. Part 2 is left as exercise. Now, what can we say about the inverse of a function? Because a function is a relation, so therefore we can talk about its inverse relation, right? So since f is a relation, this is what I have just said a while ago, it has an inverse relation. What can keep this inverse relation from being a function? Okay, first, what can happen is that if this is my A and B, we just know that f is a function, correct? So if f is a function, it's possible that you have, say this goes to this and this goes to this. So it's possible that you have extra elements in B, correct? So remember that f is a function from A to B. If we now look at the relation f inverse, remember that it has to be from B to A. It's a relation from B to A. Can f inverse be a function in this way? No, because f inverse will have domain B, but there are elements in the domain which do not have corresponding entries in its codomain. Correct? So in that case, f inverse is not a function. Okay? Remember, for you to be a function, every element in the domain, B is the domain of f inverse, correct? It should go to a corresponding element in its codomain. Now, second, it can also happen, just like what happened here, some element of B is a second coordinate of more than one ordered pair in F. So just like what happened here, A1 and A2, it gets mapped to B. This is a function, correct? This is the definition of a function. It's possible to have two elements in F to go, it's possible to have two elements in the domain to go to just one element in its codomain. However, if you look at it from B to A, because if we are now having the inverse relation, F inverse, what this means is that B will now go to A1 and A2. This is for the function F inverse. And in that case, we have one to many, correct? So that means F inverse will also be not a function. Alright? So number 1 is saying that there should be no extra elements in B. Okay, what does it mean if there are no extra elements in B? You have it here, everything should go to like that, right? No extra elements in B. What is another way of saying that? It means that F is surjective, correct? Because all elements in B should be the image of at least one element in A. Number 2 is saying that you cannot have this configuration, correct? Oops, by the way, this one is not possible. You cannot have one to many. So wait, maybe I should just have like this and another element to go here. There, F is surjective. However, if this is the case, this is still not a function because there are two elements in A which goes to the same element in B, correct? So we do not want this. So if that's the case, what do we want about our function F? We want F to be 1 to 1. F must be 1 to 1. So therefore, what have we seen here? For a function to have an inverse relation, which is also a function, the function f must be both surjective and one-to-one. In other words, the function f must be bijective. So there, for the inverse relation to be a function, each element of B should be the second coordinate of exactly one ordered pair in F. And this is equivalent in saying that F is bijective. How do bijective functions look like? So you have this one, right? This is a bijective function. Both one-to-one and surjective. No extra elements in B. Okay? So this is our big theorem. If f is a function, then the inverse relation will be a function if and only if f is a bijection. Now, we have just shown it using diagrams, but of course, we have to give a formal proof. Okay, so for our proof, again, let me just copy the premise. Let f be from A to B. And then, we will first prove one direction. So suppose that f is bijective. We want to show that if f is bijective, then f inverse is a function. So show that f inverse is a function. Okay, what is the definition of, what does it mean for f inverse to be a function? Let me just write it here. Our f inverse is from B to A. This is from B to A. Okay, what does it mean for f inverse to be a function? For every element in the domain, so we want to show that for all B in the domain, there exists a unique element A in capital A, that's the codomain, such that BA is an element of f inverse. What are we doing here? So remember the definition of a function. Your f inverse is from B to A, correct? So therefore, that is why when we get an element here in B, we want to show that this goes to exactly one element in A. Alright, so first, let us show the existence, correct? Why is it true that, let us first find this corresponding element in A. What do you think is that? This is my f inverse from B to A, but my function f, just so that you can imagine it, my f is a function from A to B. What do we know about our f? F is bijective, so in particular, it is surjective, correct? So when you get an element here in B, okay, let me just draw it in this way. This is just the same. I just want you to, I know that you are more comfortable when we draw f like this from A to B. So here we have a B here, right? But f is surjective because it is bijective. So since f is surjective, it means that this B here can be written as the image of some element in A. So B is equal to f of a for some a in capital A. That is a definition of a function being surjective. When you get any element in its codomain, you can always find an element in the domain such that it goes to this element. There are no extra elements in B. All the elements here will always be second coordinates. Okay, but what does it mean for B to be equal to f of A? That's another way of saying that AB is an element of F, which is the same as BA element of F inverse. So we have just shown the existence part. Now for the uniqueness, okay, how do you show that there exists exactly one A here? So suppose that there are two, right? So A1 and A2, and suppose that they are second coordinates. What do we want to show for uniqueness? We want to show that these two are equal. So let's write that. So suppose A1 and A2 are elements of A such that BA1 and BA2 is an element, they are both elements of F inverse. I will no longer write in sentences. Take note that this is equivalent in saying that A1b and A2b are elements of F. So let me just draw it here. So I have A1 and A2 there. Correct? Because A1 goes to B, A2 goes to B under the function F. But what do we know about F? F is injective. Let me just write it another way. This means that F of A1 is equal to B, and this is also the same as F of A2. What do we know about F? F is injective. So this cannot happen, correct, if they are different. Remember that for F to be injective, if two images are equal, then the images must be the same. So I will write here, since F is injective, the images, the pre-images I mean, must be the same. Alright, so remember that if you have an injective function, it's as if you can cancel, correct? That is the how you can also imagine injective function. You can only cancel the function sort of if the function is injective. That is the reason why when you have e to the x equals e to the y, then you have x is equal to y, correct? And why is that? Because our function here is e to the x, and this is injective. This is 1-to-1. So anyway, we have just shown here that if F is bijective, then our function, I mean our relation, so let me just write here, therefore we have shown that F inverse is a function. Now for the other way around, that is left as an exercise. So prove, so exercise, show that if F inverse is a function, then F is bijective. Next, let us consider the following function. This is just the linear function f of x equals 2x plus 1. So as a set of ordered pairs, this is just a set of all x, y, such that x is in R and y, the y coordinate, is equal to 2x plus 1. So therefore, the inverse function is the set of all yx. There is no extra parenthesis here. The set of all yx such that x is in R, and of course we still have y equals 2x plus 1. But of course, we can also write this in such a way we always want the second coordinate to depend on the first coordinate, correct? So what do we have here? So when we solve for x here, we get that x is equal to y minus 1 all over 2. Y is a real number. And we now therefore write the inverse as f inverse of y. The second coordinate is given by, that's the reason why we always want the second coordinate to depend on the first coordinate, because that this is our output. F inverse y is y minus 1 all over 2. So therefore, if a function f of x equals y is given by a simple rule, all we have to do is we are solving for x in terms of y, and this gives us the rule f inverse y for the inverse relation. Now here's another theorem for us. Suppose that we have a bijective function. Remember that we cannot talk about the inverse of a function if the function itself is not bijective. So number one is saying that the inverse of a function is just the original function. And if f is bijective, then its inverse function is also bijective. Number 3 is saying that 3 and 4 actually, it is saying that when we compose f with its inverse, then we get the identity function. Of course, this will depend on whichever comes first. If we start with f, then this composition is from A to A. So therefore, it will be equal to the identity function on A. If we started with f inverse b, we started out with b and we will end at b. So therefore, we will end up with identity on b. And that is the reason why we sort of cancel, correct? So this is what we have, what you learn, correct? If you have f inverse circle f of x, is what you learn from algebra. This is equal to x because of these two properties. Anyway, so let us prove this. Okay, our assumption here is that f is bijective. Let us prove one. We want to show that f inverse, the inverse of the inverse function is the function itself. How do we show that two functions are equal? Show that they have the same domain and codomain, and that they have the same behavior, right? What do I mean by behavior? It maps an element. The images of an element will be the same. So of course our f here is from A to B, so f inverse will be from B to A, and therefore the inverse of this will also be from A to B. So f and f inverse have both domain A and codomain B. In order to show that the two sets, we want to show that f and f inverse are basically the same set, correct? So we will show that AB, f, this should be inverse. Okay, we want to show that AB is an element of f inverse if and only if AB is an element of f. So this is what we want to show, just so that you know where we are going. Take note that this one is saying that if I start with, if AB is an element of f inverse, then AB is an element of f. I mean, this is again, there should be another inverse there. So this direction is telling us that F inverse inverse is a subset of F, and the other direction, it's saying that if we start with an arbitrary element of F, then we will end up with an element in F inverse F inverse. That is what we are doing there. Okay, so let us show that this is really true. So we have AB is an element of the inverse of F. So this means that when we invert, this is an element of F inverse, correct? Okay, remember, if we have, let me just write CD, you might be confused there. If you have CD, element of F inverse, what does this mean? When you invert DC, that is an element of this function F, correct? So that is what we did there. AB is an element of F inverse inverse. That means when we invert, BA is an element of F inverse. Okay? Now, continuing. Same argument, BA is an element of F inverse. That means AB, when I invert, that is an element of F. So we have just shown this one. So therefore, F is the same as F inverse inverse. Next, we want to show that the inverse function is a bijective function. So for number 2, we already have that F is bijective. For number 2, we want to show that F inverse from B to A is also bijective. We already know that F inverse is a function, correct? B to A is bijective. Now from part 1, we know that we have shown that F inverse, the inverse of the inverse is equal to F. And of course, F is a function. But we view F here as the inverse of the function F inverse. What do we know when the inverse is a function? It means that the original function is bijective. So that is from, so since, let me just write that, since F is the inverse of F inverse and F is a function, it only means that F inverse is bijective. You might be confused with that. Let me just write it as follows. So this is saying that, let me use star and heart. So for example, star inverse is a function. This is our previous theorem. If and only if star is bijective, correct? Correct? This is our theorem. If the inverse is a function, then the original function, this function over here, must be bijective. So here, F is the inverse of F inverse. So therefore, this is a function. So therefore, F inverse must be bijective. Next, we will show that these two functions are equal. I will prove 3, and then this is left as exercise. So going back, what do we want to show again? Maybe I will just prove 3 here so that we can see it. First, F inverse circle F and identity function on A have the same domain and same codomain. They're both equal to A. Same domain and same codomain. So we want to show that when you get an arbitrary element in the domain, what this function does is that it will map it to the same image of the identity function. So that is, this is what we want to show for all A in capital A. We want to show that F inverse circle F of A is the same as identity function. Correct? And this is equal to A, right? Okay, so this is what we want to show. So therefore, we start with, this is actually the third condition, right? For two functions to be the same, to be equal. Let A be an element of capital A. Now, we want to consider F inverse circle F of A. So F inverse circle F of A is equal to F inverse of F of A. Now, I will just give a name for F of A. F of A resides in what set? F of A resides in set B, correct? So I will just make a special name for it. Let B be equal to F of A. So I will now plug that in there. I will no longer use sentences. So I now have F inverse of B. Okay, what is this equal to? Now from here, B is equal to F of A. This means that AB is an element of F, and when we invert, BA is an element of F inverse. So always remember now, this means that F inverse of B is equal to A. So I will erase this. So since here, B is equal to F of A, so that means that F inverse of B is equal to A. So F inverse of B is equal to A. But then, what have we shown there? This is equal to F inverse of F of A, but this is the same as, maybe I should use that. Let me just erase this here and put it here. So I have F inverse of B, but from here, F inverse of B is equal to A. And this is the image of A under the function identity on A. So we have just shown this. This is equal to this. So next, suppose now that we have two functions f and g. F is a function from A to B and g is a function from B to A. The first part is saying that g is the inverse of f if and only if when you compose g with f or f circle g, you get that two identity functions. The second one is saying that if we already know that our function is bijective, then g is the inverse of the function f if and only if at least one of these are true. So this actually saves us time because for number one, it says that for a function to be the inverse of another function, you have to show that both of these are true. But if you already know that the function is bijective, all you need to show is just one equality. Okay, now part 1 also says that we can show that two functions are bijective when we can show that they are inverses of each other. Okay? Because if they are inverses of each other, then definitely the two functions must be bijective. Now, for the first part, it actually follows from 3 and 4 because remember that, what do we want there? Your assumption, we are proving this part. If G is equal to F inverse, then, so proof of 1, so we are showing that we are supposing that G is equal to F inverse. Is it true that G circle F is equal to the identity A? If G is equal to F inverse, I will just replace G by F inverse. And this is definitely identity A, and F circle G will now be F circle F inverse, and this is equal to identity function on B by theorem. What theorem is that? That's theorem 3, parts 3 and 4. By theorem 3, parts 3 and 4. Okay, next, we want to show that is one direction. For the other direction, what is it? Let me just write it on the next page. For the other direction, so we are supposing that what is that again? G circle F is the identity function. G circle F is the identity function on A, and F circle G is equal to the identity function on B. We want to show that G is equal to F inverse. Now, in the first place, I want to show that F inverse is a function. How do we show that F is a function? We must first show that F is bijective, correct? For F inverse to be a function. Because we cannot prove that these two functions are equal. Yours, G is a function here. So in the first place, F inverse must be a function as well for us to be able to compare them. First, show that F is bijective. How will we make use of the given? Now, as an exercise, verify that the identity functions are bijective. They are both one-to-one and onto. Now, if we look at G circle F equals identity A, since G circle F is equal to the identity function A, and what will we make use of the bijectivity? Is it one-to-one or onto? We want to show that F is one-to-one, okay? So this identity function is one-to-one. Then by our theorem on lecture 40, if the composition of two functions is one-to-one, then the first function that you applied must be one-to-one. Correct? Moreover, since now I will make use of this, F circle G is onto or surjective by our theorem also in lecture 40, the second function is also surjective. F is surjective, and therefore F is bijective, and so F inverse is a function. Now, I want to show that G is equal to F inverse. Now, they both have the same. So, our F inverse is from B to A, and G is also from B to A. So, therefore, their domain and codomain will be the same. So, all we need to do is to show that they are really equal. We now write F inverse as F inverse circle identity function on B. Why is it identity function on B? because that's identity function on B is from B to B and then B to A. Remember, the identity function is the identity. So when you compose it with a function, you still get the function itself. Now, we will write identity function on B as, so this is circle. Identity function on B is F circle G. Now, since composition of functions is associative, I can write it as F inverse circle F circle of G. But we have already seen that F inverse circle F is the identity function on A. That is slide 14 over here. That's theorem 3. When you compose the inverse of a function, you just get the identity function and then you just have to determine what set that is. So this is identity function on A and then circle of G. But when you compose the identity function with a function, you just get the function itself. So therefore, we have just shown that F inverse is the same as the function G. Now, part 2 is left as exercise. Okay, here is an example of an application of the theorem. Suppose we have this piecewise function, h of x, and this is known to be 1-to-1 and on to R. So meaning to say our h is from R to R. Yes, that is true because how does the graph look like? We have when x is less than or equal to 0, it's x squared plus 2. So this part, and then when x is positive, it is 2 minus x squared. So it's this half of the parabola. Okay, so it's really 1-to-1 and onto. Okay, let us prove that h inverse is equal to this function here. Now, we have already stated here that h is already bijective. So, therefore, according to our theorem, okay, if the function is already bijective, all you need to do is to show one of these two equalities. Okay, so in this case, so I will say that since h is bijective, it suffices to show that, what will we use? K circle h is equal to the identity function on R. Or equivalently, this means that K circle h of x is equal to x for all x in R. Again, they already have the same domain and codomain, so they're all equal to R. Okay, so let us now compute K circle h of x. So for the first case, so since we have a piecewise function and we are first applying h, so for our first case, x is less than or equal to 0. So we have k of h of x, and our x is less than or equal to 0, so we will make use of x squared plus 2. But what can you say about x squared plus 2? This is greater than or equal to 2. The input is greater than or equal to 2, so therefore when applying k, we make use of this. So this is negative square root of x squared plus 2 minus 2. And this is negative square root of x squared. What is the square root of x squared? That's not x class. That is the absolute value of x. And since x is less than, if x is equal to 0, then this is already 0. But let us just look at this. When x is less than 0, the absolute value of x is negative of x, and that is equal to x. So for case 2, that is left as exercise. So just show that when you apply k circle h of x, you also get x. For our last slide, suppose that we have these two functions. Prove that f and g are bijective by showing that g and f are inverse functions. This is again another exercise. And how do we show that they are inverse functions? All we have to do is to show that f circle g of x is equal to x, and g circle f of x is equal to x for all x in R. So that shows that they are inverses of each other, so therefore both of them are bijective.